How's it going, ladies and gentlemen? Mr. Donahue here once again. This time we're going to take a look at calculations with KEQ. So our objectives will be to use the equilibrium constant in stoichiometry to determine equilibrium concentrations for the compounds involved in a chemical equilibrium. That's a mouthful. So the big idea is that we often don't know the equilibrium values for all the species involved in an equilibrium, but if we know the initial and the final concentration of at least one species involved, we can use stoichiometry to determine the rest. So this is best represented with an icebox table, which is basically just for the initial, the change, and the equilibrium. So we make a little table. We have our initial, our change, and our equilibrium values for X, Y, whatever species are involved. And then we can put in the numbers as we figure them out. So here's an example problem. We have H2O liquid reacting with NH3 aqueous and making NH4 plus aqueous and OH minus aqueous. So maybe we know the initial concentration of NH3. We started off, and this was our initial concentration, and we know that we didn't start with any of the product because we just added the NH3 to the liquid. So how do we figure out the value for the KEQ? Well, first step is going to be to figure out what the KEQ expression is going to be. So again, it's going to be the concentration of NH4 plus to the first power times the concentration of OH minus to the first power, because I'm looking up here, right? All over the concentration of NH3 aqueous to the first power. Remember, the H2O liquid drops out because it's a pure substance. And now we got to figure out, well, what are those values at equilibrium? Well, I know the concentration of one of them. Maybe I have a pH probe and I was able to measure the OH minus concentration. Well, how did I go from 0 to 4.64 times 10 to the minus 4? Well, in order for that to have happened, I had to have created 4.64 times 10 to the minus 4 hydroxide ions, right? So what does that mean for the NH4? How did the NH4 change? Well, I can take a look at the hydroxide ion to the NH4 plus ion ratio. It's a 1-to-1. So whatever change is happening to OH minus, it's happening to NH4 plus. So NH4 plus must have also increased by 4.64 times 10 to the minus 4. And then how's that compared to NH3? Well, fortunately enough, NH3 is also a 1-to-1 ratio, except it's a reactant. So if I'm making NH4 plus, I am using up NH3. So its concentration, its change was negative 4.64 times 10 to the minus 4 molar. So when I do that math, I'm going to have to substitute in those values into my KEQ expression. So I got the concentration of NH4 plus, which I figured out to be 4.64 times 10 to the minus 4, times the hydroxide ion concentration, which is the same thing, 4.64 times 10 to the minus 4, all over the concentration of NH3, which when I do that math at equilibrium, that's going to be 0.0119 molar. So that's going to be in my denominator. And when I do that math, I plug and I chug and I get 2.15 times 10 to the minus 7. So that is going to be my KEQ value at equilibrium for that. Alright, so what about a problem like this? Try it. I dare you. Pause it. Come back to it. Alright, so a mixture of 0.2 moles of CO2 and 0.1 moles of H2 and 0.1600 moles of H2O is added to a 2-liter vessel at 500 Kelvin. At equilibrium, the pressure of H2O is 3.51 atmospheres. What is the KEQ? Well, first steps first. If I want to talk about how much stuff got used up, I'm going to have to convert this atmospheres to moles. So I'm going to have to use that whole PV equals nRT formula, and I want to solve for N given 3.51 atmospheres for my pressure. And that's where I get the 0.171 moles. So how did H2O, starting with 0.16 moles, end up with 0.171 moles? Well, it must have gone up 0.011 moles. So now once I figured that out, I can start to figure out what happened to the rest of them. Well, CO is also a product, so it's going to do whatever H2O did. If I made more H2O, I'm going to make more CO because they're on the same side of the equation. So it's going to change the same amount because it is a 1-to-1 ratio for those coefficients. So at equilibrium, I'm going to have this 0.011 moles of CO. What about H2? Well, H2 is on the reactant side, so it's going to do the opposite of whatever happened to water. So it's going to subtract 0.011 moles. Again, it's a 1-to-1 ratio between them, so the amount of change is the same. So I end up with 0.089 moles of H2. And I do the same thing for CO2. CO2 is also going to be a decrease. It's getting used up, so it lost 0.011 moles. Again, it's a 1-to-1 ratio, so the magnitude of the change is the same. So at equilibrium, I have 0.189 moles. Now, typically, KEQ, I got some gases. My KEQ expression is going to be the pressure of CO times the pressure of H2O all over the pressure of H2 times the pressure of CO2. So we're talking about pressures, and I have moles, so be on the safe side. Again, you're going to use the old PIV-NERT, PV equals nRT. So the pressure is going to equal nRT on V, and you're going to do that for the moles. So let's take a look at this for carbon monoxide, CO. Well, I have 0.011 moles. I'm going to times that by R, which is 0.08206 times the temperature of 500 Kelvin, all over the volume of 2.000 liters. And the pressure for that one, I'm going to get to be 0.226 atmospheres. So 0.226 atmospheres at equilibrium. And I'm going to do the same process for the rest of those. All right, it's the same process, different answers because I got different numbers of moles. This is going to be 1.83 atmospheres, and this is going to be 3.88 atmospheres. So now I can just plug and chug. The pressure of CO was 0.226 atmospheres times, actually, let me just get rid of those units, times 3.51 divided by pressure of H2 was 1.83 times that 3.88, and when I plug and chug and get my final answer, it comes out to be 0.11. So summarize. Can you describe how to use the equilibrium constant in stoichiometry to determine equilibrium concentrations for the compounds involved in the chemical equilibrium? I hope you can. If not, too bad. Okay, bye.